Hi, this is on computational hardness needed for quantum cryptography, and this is joint work with Zvika, Brakerski, and Canetti. So let me start by telling you about the computational hardness for classical cryptography. And there is this very central notion called one-way functions, which are functions that are easy to compute, but hard to invert. And on one hand, even the existence of one-way functions already allow you to do a lot of very non-trivial computational cryptography. This includes secret key encryption, signatures, zero knowledge, and so on. But more importantly, on the other hand, if you take virtually any cryptography that is information theoretically impossible, so non-trivial encryption, commitment, or even more fancy primitives like multi-party computations, it turns out that they would all imply the existence of one-way functions. So having one-way functions are necessary for constructing this kind of computational cryptography. And at least for the theory of cryptography, it is a very important question to understand what are the computational hardness needed for instantiating various cryptography. So after decades of cryptographic research, now we have a somewhat good understanding of the landscape of classical cryptography. And there is this very influential terminology by Impagliazzo, which is Impagliazzo's spy world. In particular, there is this world that he called minicrypt, where one-way function exists, but not any other kind of more fancy cryptography. And as I already mentioned, even having one-way functions, you can already do a lot of very meaningful cryptography. But on the one hand, this also tells you that we are not living in the world that Impagliazzo calls algorithmica, where P equals NP. And as we know, the problem of whether P equals NP is actually a very long-standing open question. And therefore, there seems to be a barrier as a consequence to proving the existence of one-way functions or the existence of all of these wonderful cryptographic protocols that we would like to do. On the other hand, there is also another world that Impagliazzo calls cryptomania, where there are more fancier cryptography that you can do. These include public key encryption, key exchange, multi-party secure computation, and so on. And they live in this separate world because it seems like you cannot construct these more fancy cryptography from only the existence of one-way functions, certainly not in a black box way. And now, let's consider quantum cryptography, where quantum cryptography simply means that even the honest parties participating in the protocol will be able to use quantum mechanics. So, for example, use quantum computers or even quantum communication. And starting from the work of BB84, we already know that once you enable quantum protocols, then you can in fact do information theoretically secure key exchange, which is something that seems to require very strong classical hardness to do, since it lies in the world of cryptomania. And subsequently, there has been a lot of work trying to study this phenomenon, notably ending in two works from last year by Bartoszek et al. And Grillo et al., where they show that you can actually do secure quantum multi-party secure computation from only the existence of quantum secure one-way functions. Furthermore, after those two works, there are a few more works where it has been demonstrated that you can, in fact, do quantum multi-party computation without even the existence of one-way functions. And the idea is that there is this notion of quantum pseudo-randomness, which turns out to be sufficient for constructing a lot of quantum computational cryptography like MPC or signature. On the other hand, these things seems to be strictly weaker than the existence of one-way functions. Notably, in the work by Kretschmer et al., they subsequently show that there is a classical oracle separation of this object called quantum of this sort of quantum pseudo-randomness from the existence of one-way functions. In particular, there is a concrete way of doing quantum pseudo-randomness without relying on the security of one-way function. In fact, it might be secure even if one-way functions do not exist. Therefore, we can see that once you start considering quantum protocols, it seems like the landscape of cryptography seems to change dramatically, since previously we have all of these cryptomania objects. Now we can all seem to be able to do them without even minicrypt. Therefore, it is a very natural question or a natural research direction to try to understand what is the landscape of the quantum cryptography. And in this work, we are going to focus on the following concrete question, which is that is there still a minimal assumption for computational quantum cryptography, just like how one-way function is considered minimal for a lot of classical computational cryptography. And the object that we are going to study in this work is called EFI pair. But first, let me introduce its classical analog, which we call EFID pair. And on a high level, the idea of EFID pair is to capture non-trivial computational indistinguishability. So a little bit more formally, this is a classical randomized algorithm that samples one of two distributions, either distribution 0 or distribution 1. Okay, and it is supposed to satisfy the following criteria, which captures the formal notion of non-trivial computational indistinguishability. The first notion is that in order for it to be useful, these distributions should be able to generate it efficiently or sampled efficiently. In other words, there is a uniform randomized algorithm G that samples either from distribution 0 or distribution 1 running in polynomial time. And in the end, it outputs some distribution over bit string, either distribution 0 or distribution 1. And the second criteria is that it's supposed to satisfy statistical farness. So distribution 0 and distribution 1 are statistically far. So in principle, there is an inefficient way of distinguishing these two distributions. And finally, these two distributions should be computationally indistinguishable. So for any efficient quantum algorithm, it will not be able to distinguish the distribution 0 from distribution 1 except with negligible advantage. And in fact, the classical version of this has already been studied by Goldreich 30 years ago, where he has shown that the existence of this object is in fact equivalent to the existence of one-way functions. And in this work, we consider the most natural quantum analog of this object, which is basically the same thing as EFID, but now we replace distributions over bit strings with distributions over quantum states, or in other words, mixed states. So now we have mixed state 0 and mixed state 1 that is supposed to satisfy non-trivial computational indistinguishability. So we have the same three criteria from before, but we suitably changed them so that they now correspond to quantum state instead of distribution over bit strings. So more specifically, we consider efficient quantum algorithm instead of randomized algorithm that generates these mixed states instead of distributions over bit strings. These two mixed states satisfy this co-farness, where the distance is captured by trace distance, which is the quantum state analog for total variation distance. And finally, they still should satisfy computational indistinguishability against quantum efficient adversaries. So one natural question you might ask about EFI is that since this is a very, very natural generalization of the classical notion EFID, shouldn't everything we know about EFID immediately carry over to EFI by suitably changing all the definitions and so on? Well, obviously this would fail at a superficial level because on the one hand, we know that the existence of EFID is in fact equivalent to the existence of one-way functions. But on the other hand, the existence of EFI pair cannot imply one-way functions, at least in the black box way, and this is because the quantum pseudo-randomness object that we talked about before does imply EFI. And combining this with the oracle separation between this and one-way function, we know that EFI, you should not be able to construct one-way functions from EFI. And this would prove to be a lot of trouble because a lot of classical equivalences between one-way functions and a lot of other mini crypto, they crucially go through the existence of one-way functions. And therefore, you cannot just take those ideas and port it over to EFI. It usually wouldn't work. But of course, you may say, maybe this is just an artifact of how you define one-way functions. Maybe if you change the one-way function definition to maybe some suitable notion of quantum one-wayness, then this issue would go away. Unfortunately, there is something even more fundamental than that that also would rule out that approach. Or at least it seems to show that that approach wouldn't work. And the reason is that there is a fundamental difference between how classical algorithms generate randomness versus how quantum algorithm does it. In particular, in order for a classical algorithm to be randomized, it has to take some random coins as input or a random tape. On the other hand, a quantum algorithm can just sample randomness by itself. As a consequence, there are a lot of classical proof techniques for approaching randomized algorithm wouldn't carry over to the quantum setting. One very commonly used technique is to assume a certain randomized algorithm is without loss of generality deterministic by convex combination. And another common technique more relevant to the setting of one-way functions is the technique of programming randomness, which means that you can take a randomized algorithm and then put arbitrary bit strings on its random tape. And this is something crucially invoked in the very phenomenal work by H.I. where you construct classical pseudo-randomness from one-way function. And therefore, in order to deal with or prove equivalences about EFI, we'll in fact use quantum techniques. So in this work, we summarize what we know about EFI in the quantum world as follows. On the one hand, the existence of EFI in the quantum setting does imply a lot of strong, meaningful quantum cryptography. These include statistically secure commitment schemes, oblivious transfer, quantum multi-party computation protocols, and furthermore, we are also able to show how to prove all of QIP or P-space using quantum computational zero-knowledge proofs. And on the flip side, we also showed that if you take all of these cryptographic primitives and consider a much weakened version, then they would also imply the existence of EFI. So the weakened version more formally means that, first of all, they does not need to satisfy any notion of statistical security. And furthermore, they only need to be secure against semi-honest adversary for a quantum version of the semi-honest setting. And finally, for MPC or two-party computation or quantum computational zero knowledge proofs, you only need to construct protocols for non-trivial functionalities or construct proofs for non-trivial languages. And all of these would in fact immediately imply the existence of EFI. And therefore, to put everything together, there seems to be a very robust equivalences between EFI and all of these quantum cryptographic objects. Okay, but let me also tell you some other things we note about EFI here. So in addition to the equivalence that I've just talked about, we argue that EFI pairs serves a similar role as one-way functions in the quantum cryptography world. In particular, like one-way functions, EFI pairs are essentially equivalent to various quantum cryptography, which we just talked about. It is very simple. In particular, there is this just one simple notion of EFI. There is no various variants of EFI. It is also very natural. In fact, its classical analog has already been studied by Goldreich 30 years ago. And there are also related quantum versions that has been studied, for example, by Watchers when he was studying a complete problem for QSDK. It is also seems pretty minimal because it is not too hard to see that it is in fact immediately implied by various quantum cryptography like quantum encryptions and various quantum pseudorandomness notions like pseudorandom states and pseudorandom unitaries. Finally, as we show in this work, EFI pair in fact serve as the linchpin for demonstrating equivalences between various quantum cryptography. Okay, so I will not have time to talk about the specific constructions of these equivalences. If you are interested, you can take a look at the paper. Let me instead conclude with some of my favorite open questions in this direction. One important open question, I think, is whether we can construct the quantum pseudorandomness objects that I've talked about before from EFI pairs. In other words, can we have a quantum analog or quantum state analog of the classical celebrated result of HILL? In particular, can we construct pseudorandom states from EFI pairs? Another conceptually very important direction to consider is to compare EFI pairs with unforgeable security, or you can call it quantum one-wayness, if you will. So these kind of objects include quantum signatures, quantum money, and so on, where the security is a search type assumption. Finally, as I mentioned earlier, we cannot prove the existence of one-way functions unconditionally due to the barrier of P versus NP. But for quantum cryptography or EFI, so far we do not have any evidence of having a barrier like what we have for classical crypto. So can we either unconditionally prove the existence of EFI pairs, or are there barriers for proving that they exist? So that's all I wanted to talk about today. Thank you very much for your attention.